Hello, I'm going to be going over my test corrections. So I'm going to start with the in-class section, and then on the right is what I submitted in class, and then on the left is my test corrections. So for the 30-second portion, for question one, I originally just wrote the dCA over dt equals RA, but I didn't clearly show where it came from or when it applies. In my corrections, I start from the general mole balance, show that in a closed, well-mixed, constant volume batch reactor, the accumulation equals the reaction rate, which gives the dCA over dt equals RA. Then I list the assumptions: no flow, constant volume, and density, perfectly mixed, and I give a specific gas phase decomposition example where the total moles and volume change. So this simple form breaks down and is variable volume analysis is needed. For question two, at first my answer about the adiabatic batch reactor was very vague, which is why I lost points. In the correction, I clearly state that there is no heat exchange, so any temperature change comes from only from reaction enthalpy. For an exothermic reaction, temperature increases as conversion goes from 0 to 75%. For an endothermic reaction, it decreases. This is tied to the adiabatic energy balance and makes it clear that the sign of delta H reaction controls how T changes. For question three, originally I only partially explained activation energy and didn't fully connect it to equilibrium or draw clear diagrams. In the corrected version on the left, I used the Arrhenius equation to show how E of A controls rate, and the delta H of the reaction is the energy difference between the reactants and the products that sets the equilibrium position. I add exothermic and endothermic reaction coordinate diagrams, then link catalysts to lowering E of A for both directions without changing the delta H or K, which is why they speed up approach to equilibrium but don't shift it. For problem four, the first time I didn't fully justify the reactor ordering or derive the form. In the correction, I used the negative 1 over RA for CA plot in order to order the systems from smallest to largest, D, A, C, B. Explain that corresponds to a second order slash normal behavior where rate drops as CA decreases, and the correctly state the PFR gives the lowest volume. Then I start from the ideal CSTR and PFR mole balances and derive that V is equal to the integral of x to x naught f of A naught over R negative RA dxa to match the Levin-Sproul analysis. Now moving to the out of class portion. In my original submission, I lost points for incomplete derivations and missing units. In the corrected version, I start with problem 1A from the general batch mole balance, and I write dNA over dt equals RAV. Substitute the RA equals negative K CA squared with CA is equal to NA over volume, separate variables, and then I integrated from NA naught to NA and solve explicitly for X using the given 48% conversion in 720 seconds, and then V equaled 1.7 meters cubed, including the proper units of meters cubed per moles times seconds. For part B, I clearly answered everything and didn't need to do anything else. Moving on to part C, D, and E. E, I got full credit for. For the CSTR in part C, I correctly apply the steady state mole balance, FA naught minus FA plus RAV equals 0, and then I use the X of A is equal to 0.48. And solve for the required volumetric flow rate V with consistent units for the PFR in part D. Instead of doing all of what I did, I just used the diagram equation slash space-time relationship and the fact that for this rate law and volume, the PFR is giving the same conversion must match the batch contact time leading to the correct V. And then in part E, I got full credit and I did not have to do anything else. For question two, I originally believe I lost points for just not organizing my data sources and not clearly justifying the DEB properties and for a kind of messy equilibrium calculation. In the corrected version for part A, I explicitly list delta H and delta G for benzene and ethylbenzene from the course handout and then obtain DEB data from a single external source, Aspen. I justify that source by comparing its B and E values to those in the handout to show consistency before using the values. For part V, I carefully calculated the delta G and the delta H And then I use them to find the equilibrium constant K at 400 and 2000 kPa and relate K to the mole fractions such partial pressures to solve for the equilibrium compositions and conversion. I wrote all the steps out again and defined that it's probably the ideal gas behavior, single reaction, and partial pressures. And I got a consistent numerical conversion on 0.61 that matches my algebra. For part C, or yes, for part C, I then changed how I solved and solved for 300 and then at 600 and how the changing temperature affects K using the Van 't Hoff and the sign of delta H and how changing pressure affects conversion for the gas phase reaction, backing it with the calculation shown. And then the corrected solution is as matches below. For problem 3, in my original work, I had kind of the right steps going. In the corrected version for the solution of part A, I wrote the rate law R equals KCA CP and express CA and CP in terms of conversion XA using the stoichiometry of A plus P, and then that goes to 3P, and then the given inlet concentrations. Then for the CSTR, use FA naught minus FA plus RV equals 0 at steady state and solve for the VSTR at 80% conversion using the proper expression for CA and CP. For the PFR, I just use the DFA over DR equals RV, convert DXA over DV equals negative RA over FA naught. Substitute the rate, integrate from 0 to 0.8 for our partial fractions to obtain the VPFR. I clearly reported both volumes. And then I went on in part B to explain that the CSTR holds the high product concentration throughout, which boosts the rate everywhere, while the PFR only builds product along the length. So under these conditions, the CSTR can be more volume efficient. I then state that the volume of the CSTR is smaller because the R is large everywhere due to it being at a high CP at the exit, and then the PFR would be the smaller volume if fed. So that concentration gradient would be better. For part E, I write the corrected recycle setup, defined the recycle ratio R, expressed inlet concentration with the recycle, and then wrote the design equation as dx over dv equals negative RA over FA naught with modified inlet, and then showed how to solve for the new overall conversion. My corrected work is as seen on the left, and then for the extra credit, I did not need to do anything because I got full credit as from before. Thank you.